Alright, so in this video I'm going to give you some background information on a couple of the applications to vectors that we are going to be encountering over the course of this year. So in class what we'll do is we'll jump around to a couple of the different chapters, and although you don't have to know a lot of detail about the concepts behind some of the physics, you'll see that we can, if by given a definition, a mathematical definition, we'll be able to use what we've currently learned about vectors, unit vector notation, the various types of operations you can do with vectors, adding, subtracting, multiplying by scalars, dot product, cross product, and they're actually built into some of the definitions of various physical concepts. So that's what we're going to cover today. The first chapter we'll look at is in Chapter 4. We will, in class, cover Chapter 2 first because that's going to introduce us to calculus, and it is the basics in kinematics, a review of what we've talked about last year. But Chapter 4 goes into depth with motion in more than one dimension, so 2 dimensions, 3 dimensions, and so making use of the unit vector notation and other vector mathematical skills are going to be important in trying to work with some of those problems. So a couple vectors that I want to introduce you to. So the first one is called the position vector, and this is just a vector that has its tail end at the origin, and it's pointing to the location of the object. So on an x, y, z coordinate system, we can draw a vector incorrectly. Let's try that again. There we go. Right, so that will have potentially some x, y, and z coordinate. So let's say okay, so there's your vector, and what we're going to call this vector is r. Now this coordinate right here, at the tip end of the vector, is going to have the coordinate x, y, z. So you have to go x over, y up, and z out. So that means if you want to write it in unit vector notation, we could represent this r vector as x, the value x, the coordinate x, I hat, plus the value y, the coordinate y, j hat, plus z, k hat. Now let's say that the object, which was originally here, is now going to move. So we might want to show that the object moves from one location to another, so the position vector will change in length or magnitude and direction. And so let's say that that's the new coordinate for the location of our object. So the object moves from this location to that location. So we can define a new vector that defines the displacement, how the change in position from r final to r initial. So let me go back here and put this as r1, and this is vector R2. So we have an initial position and then a final position. So what we can do is draw a vector that has its tail end where R1 started and tip towards R2. So this is what we're going to call the displacement vector. So displacement's delta R. And so that's, again, the general trend is that the object is moving from here to there. The object could have had some path that eventually took it to this position, but remember, the displacement, like you learned last year, only cares about where you started and where you ended up. So this is the displacement vector. Now, how is the displacement related to R1 and R2? Well, if I can try to switch these vectors around, you should already know the answer to this, but we're going to just double check to make sure. If we were to take these three vectors, let's say it was tip to tail. This is R2 and this is R1. So let's say if it was R1 plus R2. It's off the screen here. R1 plus R2 would get you a vector that has this length. So that doesn't look right. So what if we said R1, how about R2 minus R1? So minus R1 would mean that I would have to flip this vector around. So let's just, instead of doing that, let's imagine that the tip end here is actually the tail end now, because I've reversed the vectors. And so this would be the same as saying R2, and this would be minus R1. So what is R2 minus R1? Well, if we look at this vector, you'll see that it gets us the resultant. So delta R is in fact R2 minus R1 in vector notation. So that's the proof to show you that. So the displacement vector, delta R, is just the vector sum of R2 plus negative R1, or in other words, R2 minus R1. So you can rewrite that in unit vector notation, where the coordinates, the components of the vector, are just going to be the displacement in the x, the displacement in the y, and the displacement in the z. The next quantity is going to be the average velocity. Well, if we already know what the definition of average velocity is. It's just distance over time, in this case displacement over time. So we have our displacement vector and we're dividing it by time. Now time's a scalar. So there you have an example of taking a scalar, which in this case would be 1 over delta t, and multiplying it by a vector. So scalar times a vector. You know from that, from what we talked about in class, that this is just a scaling factor. So that means that if this quantity is positive, that it shouldn't change the direction of the delta r vector. If it was negative, it could flip the vector to face the other way, 180 degrees, but it's not going to change the angle. But time's never going to be negative for us here in general, so there shouldn't be a reason why this vector would be pointing in the opposite direction. But notice that if time was negative, maybe you're going back in time, that instead of the object moving this way, that flipping the arrow around would mean that the object would be moving in the opposite direction, which would make sense if you run the situation in reverse. So the only thing that this does is scale delta r vector a little bit differently. So if this is a number greater than 1, it'll make this vector bigger, and if this number is less than 1, then it'll make this vector smaller. But in general, the delta r vector and the average velocity vector are going to be in the same direction. So be something like this, right? And so that purple arrow represents V average. The average acceleration vector, similar situation. Now, if you know what the change in the velocity is, so this is a value for the velocity. This would be knowing what two values of the velocity are. So you have some v2 minus v1 over delta t. Then you can determine what the acceleration vector will look like. So if v2 is larger than v1, then that means you're speeding up and you get a positive value, and so the acceleration would be indicating that the object is picking up speed. But we'll go into more details about that at a later date. Alright, so then in Chapter 5 we start to deal with force, and we know lots about forces from last year. We know from Newton's second law that F equals ma, fun equals ma. So this follows that if you know what the acceleration vector looks like, then you multiply it by mass, which is a scalar, and that produces a new vector. So if you have an acceleration vector that looks like this, and you multiply by the mass, and the mass is greater than 1, then it'll produce a force vector which will be in the same direction but just larger. If the mass was smaller than 1, then the force vector would be smaller than the acceleration vector, but they will be in the same direction, and because mass cannot be negative, they will always be pointing in the same direction. Now, when we find fun, remember fun is the sum of all the forces. So, but it's the vector sum. So what we normally call fun, which is the same as F net, which is the same as the sum of all the forces, is really a vector sum. So that means it's F1 plus F2 plus all the way up to whatever force you have in your system. But those forces add together in the vector way. So you have all these forces acting on an object. So let's say you have a free body diagram. And let's see. And we have, let's say we have some gravity here. We got a normal force. We have some tension and maybe a little bit of friction. we want to know what the unbalanced force is. Now, we normally take it to be in separate directions. We look at what the unbalanced force is in the x direction, what the unbalanced force is in the y direction. You can do this a little bit more comprehensively, although that's a perfectly good strategy. But if you want to look at it in all the dimensions at once, you can just find the vector sum, and that is easy for me to do if I am using the software here, because I can now move and it doesn't matter which order, I just add these all tip to tail. So I can do this. Let's put this guy in first. So what's the unbalanced force? So remember that to draw the unbalanced force, you have to go from the tail end of the first arrow in your tip to tail to the tip end of the last arrow in your tip to tail. So that's your unbalanced force vector, which makes sense because so what that's saying is that when it's all said and done, all these forces produce an effect as if you just had this one blue force that was wanting the object to go to the right, trying to accelerate it to the right. So if we go back to the way it originally looked, it makes sense because the forces in the y direction are balanced, so they don't contribute to any change in motion up and down, but the forces are unbalanced left or right, left and right. So you don't get the full effect of the tension because you have some of the friction pulling back the object a little bit, restricting it from accelerating as quickly, but at the same time there is still plenty left over to accelerate the object to the right. So that's how we use vectors to represent forces. Alright, the last topics have to apply the various products that we learned between two vectors. We've already talked about in class work as being a dot product between force and some displacement vector. I'll call that delta r since you know what that means now. And so you can find this in two ways. You could figure out the magnitude of f times the magnitude of r times the cosine of the angle between them, or you can find out the components if you had it in component notation. So this would be fx times delta x plus fy delta y plus fz delta z. Torque is the force analog when we talk about motion, rotational motion. So torque is a vector, and you can get torque by taking a position vector r and crossing it with the force vector F. R is just the X, Y, Z components. So you could find the magnitude of the torque by doing magnitude of R times the magnitude of F times the sine of the angle between them, and use right hand rule to figure out the direction. Or if you knew the components, you could set up a matrix ijk, write in the coordinates of R and the components of F. Angular momentum is the rotational analog to linear momentum, and so it takes the r vector and crosses it with the momentum vector. Momentum is mass times velocity, so momentum itself is a scalar times a vector. So you can rewrite this in a couple different ways. For one, you can do r cross and substitute in m times v. Now m is just a scalar and it's not changing, so in most cases you could do m and then r cross v. If m was changing, then it gets a little bit more complicated, but that's one way of doing it. You could use sort of this method to find the magnitude of L. Or you can do the matrix form to find the whole vector, and ijk, the coordinates of r, and then if you didn't take out the mass, if you wanted to just use the components of the momentum vector, you have px, py, pz. If you took the mass out, then you'd have vx, vy, vz. And the mass can be substituted in later. Alright, if you have any questions, bring them up in class. Thanks.